All right, let's get started. Those are both kind of small. Let me see if I can find a bigger piece. Okay, so we'll start with a quick recap, very similar recap to what we did last time, because what we're interested in today, well, maybe I'll talk high level about what we're going to do today. What we're going to do today is we're going to be talking about properties of a boundary of a set now. And the boundary of a set is going to be very intuitive. It's going to be the very edge of the set. Now you'll see exactly how we define our boundary. We're going to define it in terms of the interior and the closure. So let's recap interior and closure real quick, make sure that those make sense, and then we'll continue from there. So first off, we have let A be a subset of a topological space X. Then the interior of A, remember we denote that with A with a circle above it, is the union of all open sets contained in A. So if any open set is a subset of A, then it's in the interior. Take all the open sets that are contained in A and union them up. That's what the interior is. Make sense? Mm-hmm. Okay. And then similarly, the union of all open sets contained in A. And then the closure of A, which is A with a line above it, is the intersection of all closed sets containing A. So now, here's A. We're looking at all the closed sets that have A inside of it and intersecting them all. We're looking for the points that are in every closed set containing A, the closure of A. Any questions with those? And so the way that we have those defined, by definition, the interior of A is always a subset of A, and the closure of A always contains A. This is the union of every open set inside of A. This is the intersection of every closed set that contains A. Those make sense? Mm-hmm. Anything weird? Okay. And then the big theorem I told you from, that we're going to use over and over again. This wasn't from last week, but the week before. Theorem 2.5. We had it stated these two ways because it's obviously going to come up again. So let's make sure we understand what it says. We're saying X is in the closure of A is logically equivalent to, remember what U sub X means?
Neighborhood.
A neighborhood of X. So X is in the closure of A if and only if every neighborhood of X intersects A. That's what this says. X is in the closure of A if and only if for every open set containing X, that open set also intersects A. Their intersection is not the empty set. They have a point in common. When you take their intersection, you get something. It's not the empty set. You get something. So there's something in both of them. So pick any U sub X you want. It has a point that's also in A. Does that make sense? Mm-hmm. And then the logically equivalent way of writing that when you use the contrapositives is, if X is not in the closure of A, then there exists an open set containing X such that that open set has no points in common with A. Their intersection is empty. So maybe one more way to help hammer this home would be to draw a picture. Here's a set A. Here's the closure of A. Here's the interior of A, right? Mm-hmm. We're saying X is in the closure of A. We'll pick a point like right there. Here's X. It's in there if and only if every open set you can draw around that point intersects A somewhere, which obviously does. Right? Mm-hmm. Feel like we got intuition back in our heads for interior and closure? Ready to continue?
Yeah.
Okay. So now the boundary. The boundary of a set. Let A be a subset of a topological space X, then the boundary of A is the set. We do this delta A. That's the symbol that we do for partial. You wouldn't know that. It's just a delta. It's a special type of delta, but just a delta, just a Greek letter. So then the boundary of A is the set, delta A, is equal to the closure of A minus the interior of A. Okay? So let's come back and look at the circle real quick. Here's A, here's the closure of A, here's the interior of A. So if I take the closure of A and I get rid of the interior of A, what am I left with? Just the outside, just that circle. Right? That's what we mean by the boundary. Very intuitive. If I were to just ask you what's the boundary of that shape, you would have already known. What's the boundary of this? It's just a circle around it. That's it. Questions?
Makes sense.
Makes sense. All right. So let's do some examples to help establish our intuition. So let's look at A. This is the numbers from -1 to 1 in the standard topology on R. With me? So, what is the closure? Not the closure. What's the boundary of A?
Just
-1 to 1.
No.
-1
Just
and
-1
1.
and 1, yeah.
-1 to 1.
No, just
That's the interior of A. So here's A interior. What's A closure?
just A.
It's just the same thing. It's just -1 to 1. So if I take all these points and I remove all these points, what am I left with? All I'm left with is the point -1 and 1. There's only 2 points in the boundary, which is exactly what you would have thought if you would have looked at the interval on a number line, right? We have this point all the way to this point. What's the boundary? This point and this point. Okay. Another example, example 2.15. We already talked about that. When we look at this picture over here, what's the boundary? It's just some circle. It's just a circle around A, right? So we don't need to do that example. Next example. Okay, let's look at the rational numbers in the standard topology on R. What's their boundary?
Everything. It's
It's
the whole numbers. Yes, numbers.
R, right? Because the closure of the rationals is
R.
R. That's what meant to be dense, right? And the interior of the rationals is
The empty set.
the empty set,
Yeah. Yes.
right? So not last week, but the week before, we said that the closure on the rationals is R, and we said that the interior on the rationals is the empty set. So I do R minus the empty set. What am I left with? R still.
The rational's interior is the empty set.
Yeah.
How does that? How
The intuition for it is, remember, if anything is in the interior of Q, then it needs to be open intervals. Because Q has to just be open sets, right?
Yeah.
So what do I need? I need to find some open interval, A to B, such that everything in that open interval is a rational. But we know that for any interval you pick, I'm always guaranteed that there's an irrational in here.
Yeah. I remember you talking.
So I can't find an open interval that's just rationals. So no open interval is a subset of the rationals. So there are no open sets that are subsets of the rationals except the empty set, obviously.
Okay, that makes sense.
Okay. Alright. Next example. Maybe a little bit of a picture to go with this one. So now we're in R2. And I'm looking at A. A is 0 crossed with -1 to 1. So all my x coordinates are 0, and all my y coordinates are going from -1 to 1. So here's -1, here's 1. We're looking at the interval this point down to here. Right? Remember, this is a Cartesian product. We're talking about the set of ordered pairs where the left-hand element comes from this set and the right-hand element comes from this set.
Yeah.
And so the graph of that is going to be these points. Anyone confused by that? Okay. So, what is the interior of this set?
1
Would
to
just
1,
be
or
just-
-1 to 1.
It'd be
It'd
-1
just
to
be
1.
the
Just
longest of the
-1 to 1, right?
Yeah.
No, you would include -1 and 1. The interior?
For the
Oh,
interior?
Sorry, I thought you were talking about the boundary.
No, the interior. What's the interior of the set?
That.
That's the interior of the set, right?
Yeah.
Wouldn't you
In
have-
R2?
No,
Yeah, wouldn't
it's
you
not.
In R2? That's not even in R2.
What?
That is.
Open sets in R2
You have to
are
give
open
a
balls.
coordinate.
Look, if you're in R2, you're a set of ordered pairs. Oh, are you talking about this as a point? You're saying the point -1, 1 is in there?
No, because it's not.
It would be.
Oops. That's up here.
No, No, points in between.
So that's not even a bunch of points in R2. We're talking about points in R2. So are you saying it's this? 0 crossed with the open interval negative 1 to 1?
No.
Maybe.
Maybe.
I think we.
How can I make, so that's this line not including these endpoints, right?
Yeah.
Is it possible for me to union up open balls and get that line without those endpoints?
No.
No.
No, how can I union up any open balls and not get any width?
You can't.
I can't.
So.
There are no open sets that are subsets of the same.
So it's the empty set.
So the interior of this thing is equal to the empty set, right? Now, what's the closure of that thing?
It's just that set.
It's just that thing. So it's its own closure. It is a closed set in R2. You might remember that we talked about that. Intervals like this are closed sets in R2. How do you know? Well, let's look at its complement real quick. So if I look at R2, so here's R2, kind of ignore everything, and I just took out these points, is that set open?
Yes. Mm-hmm.
Yes. It's this open plane, union with this open plane, intersected with this open plane, intersected with this open plane, or union with, sorry.
Mm-hmm.
Right?
Yeah.
So you union up 4 open planes, this is what you're left with, that's open. So its complement is closed. So over here I'm saying everything except these lines. Here I'm saying everything except these points. Here I'm saying only these points. So if everything except those points is open, then just those points is closed. Right?
Okay.
And so what is what's the boundary of that?
Just that set.
It's just a set again. It's just A. Right?
Okay, that makes sense.
Okay, yep, that makes sense.
Okay.
That's a lot of sense.
Yeah. Just trying to establish intuition for boundaries of different sets. Okay. So now let's look at A equal to the set -1, 1, that same interval. But now we're in the discrete topology on R. What's the discrete topology?
On R. I forgot.
It's just the power set.
The power set. It's the set of all possible subsets.
Okay.
That's what the topology is. So, what's the interior of this set?
Just that.
It's this set, right?
Yeah.
What is the topology? The set of all possible subsets of the real numbers. Is this a possible subset of the real numbers?
Mm-hmm.
Yeah.
Then it's open,
Right.
Yep.
right? And this is the union of all open sets contained in A. Is this an open set contained in A?
Mm-hmm.
Yep.
All right, there's your interior.
So what's
But
the
now
closure?
what's the closure?
Is it the closure the same set?
It's the same set. How do I know if this set is closed? I look at its complement and see if it's open. Is the complement of this thing a subset of real numbers?
Yeah.
Yep, therefore this thing's closed. So it's open and closed. So,
The boundary is
in
zero.
this case, A closure is equal to A interior. They're all equal, right?
Therefore.
And so now the closure
minus
minus the interior is
empty.
the empty set. Perfect. Next. A equal to the interval -1 to 1 in the lower limit topology. You remember the lower limit topology?
No.
It's where your basis elements look like this. A, B, not including that side. So standard topology, your basis elements look like this. Lower limit topology, we include the A on the left-hand side.
So you're including the -1 but not including the 1.
Correct.
Okay.
Well, this is a basis element. Yes, if that's what you're saying.
Well, so wouldn't that be
would
the
its
interior?
Wonderful. And what's the closure?
A, right?
The whole set A is the closure.
Yeah.
So what's the boundary?
Just B. So 1, yeah.
Yeah, just one.
Wow, look at us.
Yeah, look at you. Okay, and then theorem. Let A be a subset of a topological space X, and let little x be any point in X. Then X is in the boundary if and only if every open set containing X intersects both A and A's complement. So let's get a picture of that real quick. We'll just look over here at this picture. So here's A, here's a closure, and we're talking about the boundary. So the boundary in this case is, well, we can just look on A, but pick any point on A's boundary now. Any point in A's boundary. Those are only points out here on the circle, like right here, right?
Mm-hmm.
There's a point X. We're saying X is in the boundary if and only if every open set I can make around X intersects A and intersects A complement. So it has points that are in A and it has points that are not in A. That's the only way it can be on the boundary. If X was in here, and it wasn't on the boundary, then I can make a small enough circle that all the points in that circle are inside of A. If X was barely off the boundary over here, then I can make a circle small enough that all the points are not in A. So it's on the boundary if and only if, no matter how small of a circle I make around there, I get points both in A and not in A. Does that appeal to the intuition?
Yeah.
So that's what we're going to prove now in a more general way, not just R2. So let's see how we want to start. We'll go this way first, whichever way that is. X. So assume X is in the boundary. Right?
Mm-hmm.
Which gives me that, just like we have it explicitly, we know that X is in a closure and X is not in A's interior, right?
Yeah.
Oh, and something that I didn't remind you of that I know we need to use for these. Theorem 2.6. Theorem 2.6 was that the complement of the closure is equal to that. I have that wrong. No, the complement of the closure is the interior of the complement. Okay, I said everything right. When I pull my complement inside, so notice we're doing the closure and then the complement, right?
Mm-hmm.
So if I want to do my complement first, then it switches my closure to an interior. So one way to think about it is, if we write these out as functions, we're talking about which one am I doing? I'm doing the closure on A complement. The closure on A complement is the same thing as the interior of A complement. So you can think about it whichever way you want. If I want to bring the complement inside the function, it switches it from an interior to a closure. Or if I want to pull the complement outside the function, it switches your closure to an interior.
Okay.
And vice versa. So if I have the closure of A and then we complement it, that's equal to the interior of A complement. You remember doing those?
Yeah.
I think so.
And we drew the pictures out to try and establish each of those in your intuition. But the way that I always remember it is just talk about moving the closure inside or outside of the interior closure function. So it just switches them. Anyway, so back to here. So X is not in the interior of A. Well, that's the same thing. So I know X is in a closure. Maybe we'll do a separate thing expanding on this. Observe X not in the interior of A is the same thing as X is in A's interior's complement, right? X not in A is the same thing as X is in the set of everything that's not the interior of A.
Okay.
Which is the same thing as X is in, if I want to pull the complement in, then we get A complement's closure.
Yeah.
You follow that?
Yeah.
And then here's where we're going to use 2.5. then by 2.5 for all u sub x intersect. Since x is in A's closure, notice what it says here. X being in the closure of a set means every neighborhood of this point, x, intersects that set. X being in the closure of a set means every neighborhood of x intersects that set. Since x is in the closure of A, then every neighborhood of x intersects A is not equal to the empty set. It intersects A. Similarly, by the exact same theorem. Right? I know that x is in a closure, and I know that x is in a complement closure.
Okay.
So every neighborhood of x, for any neighborhood of x you pick, it intersects A, that's because of this, and it intersects A's complement, that's because of this. So we've done the first way. We've just really shown that if you take some boundary point, then every open set containing it intersects both A and A complement. And now we need to go the other way. You with me?
Mm-hmm.
And we probably could have shown these as just equal, because I think the other way is going to be identical. Now, assume that's not showing such equal. Never mind. Now assume for all u sub x intersect A is not empty, and u sub x intersect A complement is not empty. Right?
Mm-hmm.
We're going this way now. Oops. We're going this way. Sorry. Just put that arrow there. Now we're just going to use 2.5 twice. Same exact thing. If every open set containing x intersects A by 2.5, I know that x is in a closure. And since every open set containing x intersects a complement, then I also know, and x is in a complement closure, right? 6, observe, x in a complement closure, it gives us that x is in what?
It's in the
X is not in the interior.
Right.
It's in
So
the
x
interior.
is in the interior's complement,
Oh.
Right.
right? And now we can say that gives us x is not in the interior.
Yes.
Yeah, I was trying to get you to make this one first, going from here to here.
Yeah.
Pull the complement out, switches your closure to the interior.
Gotcha.
Okay? So, if x is in a closure and x is not in a interior, therefore, x is in a closure minus a interior. It's in here and not in here, which is the boundary of A. And we're done. Any questions on anything there?
Nope.
Makes sense.
Anything not straightforward? Ooh. Okay. Move the camera. All right. So now, Theorem 2.15, last thing we're covering today. Let A be a subset of a topological space X, then we're showing that these 7 properties hold. And I'm just going to prove them one at a time and erase them. So first we're going to prove that the closure is closed. Or that, sorry, not the closure. The boundary is closed. So that's what we're trying to do. I'm going to start all my proofs with let A be a topological subset, or let A be a subset of a topological space X. So right now we're proving 1.
You're showing that a boundary is closed.
Yep, showing that the boundary is closed. So in other words, in R2, just those points, that's a closed set. Which makes sense, right?
Yeah.
Everything inside, that's open. Everything outside, that's open. Union those up,
Still open.
still open. Okay, so 2. Maybe we'll write out the complement explicitly. So in order to show that this is closed, I need to show its complement is open. So I need to show that x minus delta A is open and we're done, right?
Yeah.
Because then this set's closed. This is the same thing as the complement, right? I'm just writing it out explicitly because I think that's going to help with how we write this to see it all. So this is equal to x minus A closure minus A interior, which is the same thing as x minus A closure union the interior. And that's because this is a subset of this. So I don't want to write out a full, all the propositional logic, but I think you will just be obvious. I have x, and I remove everything in A complement that's not in the interior. I remove everything in the complement that's not in the interior is the same thing as removing everything in the complement and then putting back the interior.
Okay.
Does that make sense?
Mm-hmm.
And then, maybe we don't need to write anymore from here. What's this set?
It's the complement of A's closure.
But what do we know about it?
It's open.
It's open. And this?
Also open.
So open and open is?
Also open.
So this is open. So delta A is
Closed.
Close.
closed.
Okay.
We showed its complement is open. Don't lose track of what we were doing.
Yeah.
Make sense?
Mm-hmm.
Yeah.
Okay. And I think you get the picture. I don't need to draw out all the nitty-gritty. Or do we?
I think you're good.
Okay?
Well, that was simple.
Yeah, I think all of these are pretty simple. Maybe 1 or 2 of them will throw us for a loop. Next one. Prove that the border is equal to the closure intersected with the closure of the complement.
Isn't it also true to say that the closure is also equal to the complement's closure? Or, no, sorry. I was thinking the borders or something. Never mind.
Okay.
I don't know what I was thinking.
I think they have the same border.
Yeah, that's what we're about to prove.
Okay, so this one we'll just do basic proving sets are equal. So I'll let x in here, so it's in there, and then vice versa. So
Okay.
let x in the boundary of A. That's the exact same thing as, I'll do this as if and only if, that way when we get to the done, reversing it would get us, show it both ways.
Okay.
So I'm going to show x in here is logically equivalent to x in there, and then run it backwards. And we're done. Okay, so let x in the boundary, that means x is in a closure, and x is not in a interior, right?
Mm-hmm.
But that's logically equivalent to, you obviously know what I'm going to do here. X is in a closure and x is in a interior complement, which is the exact same thing as x is in a closure and x is in a complement closure. Now we're done. Right?
Yep.
Make sense? Okay. Next, show that the boundary intersected with the interior is empty. Well, that one's just obvious. The boundary is the closure minus the interior.
Yeah.
So we take the closure, remove the interior, and then intersect it with the interior. It's the empty set. I don't think we even need to write that, do we?
No.
I think
Okay.
that's pretty straight, yeah.
So that one's straightforward. Let's go to the next one. The next one's almost as straightforward, but maybe writing it out will help a little. Observe. So we're doing this one, right? So delta A union A interior is the exact same thing as A closure minus the interior union the interior, which is obviously just equal to A closure. Could have made those equal signs. Right?
Yeah.
Take A, remove the interior, and then put it back. Okay. 5. The closure is a subset of A if and only if A is closed. Okay, that one seems harder. So I'll go this way first. Assume delta A is a subset of A. And that's the exact same thing as, maybe we just need implication arrows here. Well, I don't know. We'll do the exact same thing. We can view them as implications if you want. So if delta A is a subset of A, that's the exact same thing as A's closure minus its interior is a subset of A. So notice, A interior is also a subset of A. Right?
Yeah.
So I know everything in the closure that's not in the interior is in A. Everything in the closure that's not in the interior is in A. But I also know that everything that's in the interior is in A. Therefore, everything in the closure is in A.
Right.
Did you follow that thinking?
Yeah.
I think so.
In other words, since this is a subset of this, then maybe we can write it. Since A interior is a subset of A, we already knew that all these points were in A, then the closure must be a subset of A. But we already know that A is always a subset of the closure. We have the closure as a subset of A, so this gives me that the closure is equal to A, which gives me A is closed. You follow that?
Yeah. Then A can only be closed.
A is closed if and only if it's equal to its closure. Yep. And it's open if and only if it's equal to its interior.
I don't see how you made the subset equal to the set. So how did you make the closure of A equal to A?
Okay. So you're saying you're confused by this step?
Yeah, isn't the closure of A just...
By definition, so back over here, for any set A is always a subset of its closure. The closure is the intersection of all closed sets containing A. So A is always in there.
Okay.
So here we showed that the closure is a subset of A. We know already, based off the definition, that A is always a subset of the closure, therefore they're equal.
Okay.
Make sense? And then, so then we got A is closed. Now let's do it the other way. Assume A is closed, or in other words, assume A is equal to A closure. Obviously, it's what we're going to use. 5. Then, let's see, what are we trying to show? We're trying to show
The boundary is a subset of A.
that the boundary is a subset of A. That's what we're trying to show. I'm going to underline that. Trying to show the boundary is a subset of A. Okay. So then, the boundary of A is equal to A closure minus A interior, right? So we took the closure and we got rid of points. So that's definitely a subset of the closure, but that's just equal to A. So A boundary is a subset of A. You follow that?
Yep.
And we're done.
That was easy.
Any questions there? Okay, and we're on to 6. Maybe right here, so I know it's in place. We did this one, so now we're doing this one, 6. Showing that the boundary intersected with A is empty if and only if A is open. So if A is equal to its interior. Oh shoot, I erased the top line. 1. Let A be a subset of a topological space X. That's big X. X. Okay. 2. So, let's go this way. Assume the interior of A intersected with A is equal to the empty set, right?
The boundary.
Yeah.
The boundary, I don't even know what I said. The boundary of A intersected with A, pretty sure I said interior somewhere.
Yeah.
The boundary of A intersected with A is the empty set. Okay, what does that give us? That gives us that A closure minus A interior intersected with A is equal to the empty set. Okay, we got some similar thinking here. So I took the closure and I got rid of its interior and I no longer had any points in A. That's what this is saying. I have the closure, get rid of the interior, now it has no points in common with A. So when I removed the interior, I removed A.
That means you remove.
So A is a subset of the interior. So that gives me that A is a subset of A interior, and then that's going to give me that A is equal to A interior.
Yeah,
Because I know that the interior is always a subset of A.
right.
Okay.
You follow the thinking there?
I think so.
Yes, but it feels like you're doing a lot of explaining and not a lot of like writing the proof out, if that makes sense. Like it feels like kind of a big jump, but I get the thinking.
Right, so what you would be writing out is, so let's look at this. So A closure minus A interior and A is false. How would we explicitly want to write this out? I mean, I don't know how else you would say it other than just explaining it with words. I don't have a good way of writing that with just sets. Because what is that? That's a set of all X such that X is in A closure and X is not in, X is in the closure and X is not in the interior and X is in A. So we know that this set is empty. We know that this set is not empty. We know that this overall set is empty. And so the only way let's see, that is equal to the empty set. Maybe the easiest way to think about this would then be to take the complement of it all and say that has to be everything. X is in the closure.
Does your textbook do it how you're doing it? Just keeps going.
The textbook didn't prove any of these.
I was mostly just wondering because your last proof when you were just doing a lot of explaining, I noticed how you could do it with just like set notation or whatever. I was just
Yeah.
wondering if you could do the same thing, but if not.
I want to say you could have done a Venn diagram proof, but then that's presupposing you're always in R2, so that doesn't really work. Yeah. I don't have a good way of writing it out so that it's completely rigorous. I'm guessing that the trick to doing it though would be taking the complements of everything and using the fact that that has to be equal to X, and then writing your complements in terms of x and getting them to cancel out. Yeah, but I think you get the obvious idea, right?
Yeah, right.
If we have a closure and we remove the interior, and now we don't have any points in A, we must have removed all the points in A. Make sense?
Yeah.
Yeah. I don't know, I'll have to think about a way to clearly write these rigorously. Maybe write just at least one of them. And it looks like these open and closed ones are the ones that we have to kind of do it weird with, 5 and 6. So if I remember, I'll try and write one of them out rigorously for next time so that we can see it. Anyways, okay, so we got A is equal to A's interior. So now let's go the other way. 3, now assume that A is open, or in other words, A is equal to A's interior. That's the same thing as it being open, right? So assume A is equal to A's interior. Then, well, obviously, then delta A intersect A or minus A interior. Oops. Oh, I'm doing two at the same time. Sorry, skipping ahead in my bad. Delta A intersect A. Delta A intersect A is equal to A closure minus A interior intersect A is equal to A closure minus A interior intersect A interior is obviously empty. The set of everything that's in here, not in here, and in here is empty.
Yeah.
Because there's an obvious contradiction. Okay, so that's how we show it that way. Oh, maybe we do something similar going the other way. Maybe you get a simple contradiction to show it's the empty set. Oh, but that's showing it's the empty set. So, never mind. Making me wonder if this would be best way to prove by contradiction. Well, I'll think about that later. But we're done with this one, right?
Yep.
So now the last one is showing that the boundary is equal to the empty set if and only if A is clopin. I've been introduced this word before. This is a common word in topology. Clopin means both closed and open. If it's a closed set and an open set, we call it a clopin set. And that is actual common terminology, and I realize I've never brought it up before, so
Here it is now.
there it is. So let's do this one.
Do you think you have words like topology, but then you run along clopin? It's like at this point, the mathematicians are getting real lazy. Overtired.
Assume that the boundary of A is equal to the empty set. That's the same thing as the closure minus the interior is the empty set, but that gives us that the closure is a subset of the interior. If I take the closure and I remove everything in the interior, and it turns out I removed everything, then everything in the closure must have been in the interior. But we know, observe that we already know that A interior is always a subset of A is a subset of A closure. So if I have the closure as a subset of the interior, and I know that the interior is always a subset of A is a subset of the closure, that's going to give me that A interior is equal to A is equal to A closure, which gives me that A is open and closed. You follow the logic there?
Yeah.
Since this is a subset of this, and this is a subset of this, these two are the same set, A sandwiched between them, therefore A is the same thing as both of them.
To show the other way, isn't it just like basically the same process, just opposite?
Probably. Let's show the other way and see if it's the same process except for opposite. Assume, oh yeah, this one's super easy. assume A is equal to A interior is equal to A closure. That's what it means for A to be open and closed.
Mhm.
Well, then that gives me that the boundary of A equal to A minus A is equal to the empty set. And we're done. Right?
Mhm.
Okay, that's it. That's all we got for today. Told you it'd be a quick class. That's the end of chapter 2. So we'll be starting chapter 3 next time. We're not going to do the application section.